Today we're going to talk about molding sand and cores, although mostly in this section, part one, we're going to be talking about sand properties and green sand. Lots of different properties of sand, and I'm going to quickly go over some of them, but all of them have some sort of an effect on how your molds are going to come out and how your castings are going to come out. So making sure to use the proper type of binder, which binder would be like a resin or clay or anything that bonds the sand together. Additives that help to give you certain properties. But some of the characteristics: compressive, tensile, permeability, refractoriness, friction with the liquid, heat transfer, binder costs, reclamation, flowability, compactability, mold density, bulk density, surface finish, durability, and expansion. So some of these things off to the right, you might not even know what they mean now. Crushes and erosion, what are those things? So we'll need to talk about those as we go here. So some of the typical sand tests will require a 2-inch diameter by 2-inch tall cylinder. So you did this in the lab, or will do this in the lab. And essentially, you need to put the right amount of sand in that little sleeve over here to the right. When I say the right amount of sand, usually you start with 165 grams, and you vary that up and down. You run it through a sieve, and then you ram, using this handle here, 3 times to produce a cylinder of sand that is 2 inches in diameter and 2 inches tall. It's a 14-pound weight, and it falls 2 inches each time you ram it. It has to be 3 rams, not any other number. Then you can take that sample and do many different tests to it. One of the tests you could do would be the mold hardness. So you can actually use this hardness tester here to read from 0 to 100. So greater than 90 means the sand's capable of being compacted, and you'll be able to get a high strength. So mold hardness is relatively closely related to green compressive strength, which is one of the main factors that you're going to be studying. And if you look here, we have this kind of older style here with a dial on it, but there is a newer digital unit. But essentially you push this against the mold or the sample, and it dents into the sample with this little kind of rounded ball on the end, and then that gets pushed up into the testing piece of testing equipment. And depending on how much it's sunk into your sample will give you a number. The deeper it sinks in, the lower the number will be. So one of the sand tests you're going to use with that 3-gram sample is permeability. Now, we don't have this tester in our lab, but essentially you put that sleeve onto this side over here, and you'll see it's actually going to suck air through the sample, and then it'll tell you basically how much air went through the sample. This is kind of interesting. This little dome on the top lifts up, and it pushes air through the sample, and it kind of measures how fast it falls under a certain weight. Okay, so if you don't have good permeability, when you put molten metal into this sand, what's going to happen is you're going to have back pressure, and that back pressure might do anything from give you a blow defect, where you have these little kind of like it would be little divots in your casting, all the way to having a actually explosion happen in some cases. Okay, so those little divots are from steam that gets ejected from the sand and actually makes a bubble on the side of your casting as it's solidifying, and you end up seeing that in your casting. So a blow defect is not one you want to have. So that's permeability. Next test you're going to talk about, this particular tester on the right is a universal sand strength machine, and it does all kinds of tests. You put different fixtures in here on this unit, and those fixtures will allow you to do certain types of tests. Let's see here. It's you take your 3-ram sample and you put it on in between some jaws or some sort of a testing apparatus over here on the right. Good green compressive strength, 20 to 40 psi. We typically get a little bit lower than that, especially with this last batch that we did, because we were low on the clay. Hold on, if I go to this, I'm going to open the hyperlink. So this is the one that you guys are going to do, the green compressive strength. Make sure that you can kind of put a preload on, but then turn the preload back to 0 and then hit the test. It's one thing you might not have done. So this particular one has like 24 psi. There's a splitting test as well, and this shear strength or splitting test gives you a better indication of the tensile strength. So the one was compressive strength, and this is kind of an indirect way of measuring tensile strength. So you see they put a slight preload on it, and they turn it back almost to 0. There it goes. So it actually sheared this in half, but it's hard to see, but it just moves slightly, and then there's where it's sheared. So these are the different types of fixtures that go on here. So that's good enough on that. Okay. So the shape of the sand grains has a large effect on the properties of the sand. Now in Wisconsin we have the best sand in the world, and it's mined all around. Taylor, Wisconsin is one place that you can get it, but it's Badger Mining. There's several different mining companies, Unimin, and they're all over Wisconsin and the areas around Wisconsin, like Michigan and Illinois, Iowa to some extent, and into Ohio. So this is why there's so many foundries in the region around Wisconsin, Michigan, and Ohio, and all those states. So the let's see here. So round sand grains, which we have, they have the minimum surface area. So a sphere has the minimum surface area for the volume. Okay, that means that there's less binder we're going to need. So things are glued together by coating the whole surface of something. So if it has a high surface area, you have to have more resin. And so you'll hear that throughout my explanations, that high surface area means a higher binder requirement, which is going to be more expensive and also can lead to problems, which we'll talk about later. But if you have to put a ton of clay on the sand in the sand in order to get them to stick together, You might have high moisture requirements, and then you might have some other problems with your castings. Good flowability means that the sand grains have to be able to flow into, let's say, a core box or into a mold or something like that. Good permeability, we talked about before. Round sand grains have good permeability because they have a lot of opening between them. They kind of just touch on one point, kind of tangent to each other. Good refractoriness, that means that they can withstand high temperatures and even cycling from low to high temperatures and back down, low, high. And then the reason for that is when they're smooth, they're less likely to have a imperfection that they'll have a crack forming. Because what happens is the sand grains will break down over time. The problem is that when you put forces on round sand grains, they sometimes have poor strength. In other words, the binder has to do all the work. If you have, and we're going to talk about the different shapes, but an angular or subangular grain, they kind of lock together. So that's why when you use gravel, like for a driveway or under concrete or something like that, they usually use very angular pieces of gravel, and under, let's say, railroad beds as well. Okay, so it doesn't have as good a strength. If you ever walk down a beach that has large stones that are all round, it's very difficult to walk because you just keep on sinking into them. But it has high rigidity, which means that the sand grains are impinging on each other, and they don't have a lot of room to move as the sand grains expand, because sand will expand slightly, and then you don't want them to expand into the cavity. So subangular are somewhere between angular and round grains, so they have some little edges on them. So your binder requirement's going to go up. The properties are somewhere between the two. Okay, angular is, it could be something that's been fractured, or just never had a chance to get rounded off by being in flowing water, or some sort of way of softening the edges. Okay, so angular sands have high surface area, so they're going to use a lot of binder. They're difficult to reclaim. What does that mean? That means that one of the ways to get the binder off the sand is to knock the grains together. But if they all have all these nooks and crannies, it's difficult to get that binder off the surface of those sand grains. We'll talk later about reclamation and how you reclaim sand. So that we're going to run out of sand at some point. And in Wisconsin, we have so much of it, a lot of times the foundries just throw it away. But in other areas where it's really expensive to get, we ship it there. So a lot of the cost is the shipping. Then they do recycle more or reclaim their sand more often. So it's got poor permeability because you have to use so much binder, and they kind of lock together, so that the air can't. There's not much space between these sand grains for the air to flow and the gases to get out of the mold. Also, it does tend to break down more because the angles on there have little points at which a crack can form. They do have good strength, however. When I say strength, what I mean by that is that the actual sand as a whole, when it's got the binder in it. So when you make a core or you make a green sand mold out of an angular sand, it'll be a little bit stronger on the green compressive strength. And it has low rigidity. So in other words, when the sand expands, it can kind of rearrange and accommodate the expansion. Next test we're going to talk about is the sieve analysis. And we have this piece of equipment. We're going to do some calculations with this. But essentially, you put 100 grams of sand at the top of that sieve on the first sieve, and then you allow the sand grains to fall as this whole thing vibrates. And eventually, the sand will be distributed on these different sized sand meshes. So basically, each one of these has a slightly different grid size. little wires in there, and that screen then allows different size sand grains to fall down. And if they make it all the way to the bottom, that means it's a really fine sand. And if it makes it part way down, it's a coarse sand. We have a kind of complicated way of telling what the distribution of those sand grains is. It's kind of an average. And then we talk about how that distribution is. So if you've taken your statistics class, you'll know that when you have a distribution, it can be a wide distribution or it can be a narrow distribution. If the hump kind of goes up really steep and we might only have most of the sand on a couple of those sieves, or it could be really broad and over a bunch of those sieves. And so how do we determine what kind of sand you have? You have an average that you find is called the AFS grain fineness number, which is the average size of sand grain that would be retained on one of these screens here. And they have numbers, by the way. And the numbers, I believe, are the number of wires per square inch, or openings per square inch, I mean. And so if you have a higher number, then it will be a finer grain sand. Now here's the way the distribution thing works. If you have 10% of the sand on one of those screens, you count it as a 1, okay? You count it as one screen. So in other words, if I have 4 of them that are over 10, it would be a 4-screen sand, or my distribution would be over 4 screens, okay? And then that would, tail off at the end. It could be, 30% on each one of those, but as long as it's above 10. If it falls between 10 and 7.5, we count it as a 1/2. So if you had 3.5 screens, you have 3 screens that are over 10%, and then 1 screen that was between 7.5 and 10% on the distribution. So typically a 3-screen sand, something like that, would be something you want. Maybe a 4-screen, but you typically 3 screens is what your distribution is, maybe 3.5. Okay, so how do we do this calculation, and what does it mean? So a fine sand, again, has a large surface area. It means you need more binder to glue it together. There's more grains that have surface area on them, so it's going to need more binder. They have poor permeability or low permeability because the air can't get between the grains. Poor refractoriness. Finer grains heat up more, so they get to a higher temperature, and they're more likely to break down, okay, with temperature. You get a rigid mold, which is more likely to have an expansion defect, because the really, really, really fine grains are all touching each other, and as the sand grains expand, they're binding. And what happens what can happen is, if there's nowhere for the sand grain, you got a flask around this holding everything in under compression, and the sand's trying to expand and it can't. What happens? The sand actually buckles and it makes a defect into your casting, and we'll talk about those defects in a little bit here. You might get a high mold density, okay? So a high mold density means that you're going to need, you have a lot of water and a lot of binder in there and a lot of sand. So if you have a high mold density, typically you have lower penetration. That means that the metal can't penetrate between the sand grains as easily. So you might get a better surface finish with a fine sand. So typically, if we're trying to do really fine work, we might have a grain fineness of something like 100 or even 120. Okay, if we're doing work that needed a lot of permeability, like gray iron castings and ductile iron castings, or even steel, they have usually really coarse grains. So you might have a grain fineness of 55, or even below that if you're doing steel, maybe 60, 55, 60. I believe the grain fineness that we use in the lab right now is 70. So, and the reason for that is we don't use green sand very often for iron, but we do use it for aluminum and brass. So, we're kind of like in the middle. We could go to slightly higher if we're trying to do our aluminum stuff, but as we go to brass and we sometimes do cast iron, we're going to run into problems then. Okay, so how did this calculation work? And this is in your book. You should be following along in your book here. But you have a sieve number, which I told you has, it's the number of openings per square inch, and then you have a multiplier for each one of these. So it's kind of like a weighted average, okay? And the number is not exactly equal to the sieve number. So it's kind of a plug and chug. You have to kind of trust that, the people before you did a proper job at trying to figure out how to weight these so that you get the distribution that you get, or the number, the average that you get, is representative of what we're trying to see. So essentially what you do is, that was the grain fineness number. So you're going to use those multipliers, and there's some math involved we're going to talk about in a second. The surface area is a little different. The multipliers for the grain fineness are always the same no matter what kind of sand we're using. And there's different kinds of sand, by the way. It's made out of different materials, either silica or olivine. There's a whole bunch of different kinds of sand that people use for foundries. They're even using synthetic sand now. So the surface area has the density is in that equation. So you need to take into account. It's because it's per gram. It's what's the surface area per gram of sand. And what's cool about this is we can actually calculate then how much binder we might need if you have variation in your grain fineness. Okay. So the surface area multiplier, you have your sieve numbers. There's another multiplier, and this is the first one here is the fineness multiplier. The second one here is the surface area multiplier. So what you would do is you take the number of grams of sand on each one of those screens, and then you'd multiply them by these multipliers, and then you add them up actually. Okay, but when we have different kinds of sand, the surface area multipliers will change. And when it doesn't matter on the fineness of the sand, those multipliers are always the same. So here's a sample calculation here. We have these sieve numbers. A lot of times you don't have sand that lands on some of those really coarse ones. I mean, like some of them are only like 5 or 6 per square inch. So they're like, a big grid, 1/4 inch openings or something. So no sand typically, stays on those. But here we have the sieve number 40 has 19 grams, so we would count that. This one, it was 99 grams total was the weight, so you have to kind of do it out of 99 instead of 100. They didn't put 100 grams in there, which is okay. You just have to do it according to how many the total grams as a percentage is. But it's pretty close, so we could see that this one, the 40, the 43, the 19 and 43 and 25 grams, those are all one sieve. And then the 8 would be a half sieve. So this is a 3.5 sieve sand, or the distribution is 3.5 screens. Okay, so what we're going to do is we're going to take our number of grams that we had, we're going to multiply it by the fineness multiplier, and then we get a number, a product. And we do that for all of the different screens, and we get all these products, and then we add all those products up, and we get a product of 4540 here. If we go down below, in order to figure out the actual grain fineness, we divide it by the number of grams of sand, and then we get a 45.4 or 0.86. So 45 is a relatively coarse sand. Now the surface area, we have to do a couple of things here. So the surface area, by the way, all of these so far are assuming that the grains are relatively round, especially for the surface area product. Okay, and that's going to be important. The next slide will show you why. But essentially, if you have a perfectly spherical thing, that's what we're going to calculate with the surface area product. Then what we have to do is we have to apply a factor that that kind of corrects for the fact that it's not exactly round. And that factor will be a higher number, so you have more surface area, right, if you have a angular sand than a round sand. But the round sand is not perfectly round, so we have a multiplier for that. So we do the same thing. We use the surface area product using the correct multipliers for the type of sand that we have. And it matters now. So you have to do two extra things on this surface area thing. First of all, we got to use the right multipliers. Okay, we take the product when we add those products up to, and we get this 10,990, and we divide it by the number of grams, and we get 111 square centimeters per gram. Okay, so we're going to go to the next slide, and if you forget to do this, you're going to get this problem wrong on the test or whatever you're doing. If it's a round sand, you're going to multiply it by 1.2. So now every sand in Wisconsin is pretty much a round sand, so we would multiply that by 1.2. Okay, and so, you know, we're going to get somewhere around, I don't know, what would that be? So that means that there's 133 square centimeters, 133 square centimeters in every gram. A gram is going to be like less than a cubic centimeter of sand. Okay, so and there's 133 square centimeters. Now, a square centimeter, if 10, 100 would be 10 by 10 square centimeters. So the surface area, just think about it. You're going to take resin or clay and you have to coat that whole surface for just that little bit of sand. So it's pretty amazing that how you can spread that resin or clay over the surface of those sand grains. It's a really thin coating and everything, but you have machines that actually have to do that work and mix them all together in order to get that surface area. It goes up very quickly. As the grain fineness gets smaller, that surface area goes up very quickly, and then what happens is you have to put more binder in, or the cores get really weak. What happens sometimes is when they put sand into the bin for our mixer or something like that, as you add it to the top, the fine grains stay in the middle, and the bigger grains roll down the side because it makes kind of a cone shape. Okay, as it fills, and what happens is all of the fine sand then is in the middle, and all the coarse sand's on the outside edge. And when you start using the sand in the hopper, the sand goes straight down first because the hopper has an opening usually right in the center. So at the beginning of the day, you'll have really, really fine sand, and the molds will fall apart because you don't have enough resin for the surface area on those grains. At the end of the day, when you're getting all the coarse sand coming in there, now the molds are hard as a rock, and you probably turned up the resin a little bit in order to compensate for the earlier part of the day, so you have these cores that don't come out of your molds and stuff like that. Same thing happens in green sand. You have problems with not enough clay. The molds aren't going to be strong enough. So what can you do on that? We actually put a baffle plate in the hopper. This really only works with dry sand, but the baffle plate, what it does is it makes the sand go through little holes, and so it kind of forms more and more of these little pyramids that redistribute and remix the sand. So it's just a little flat plate in our hopper that does that. We actually added that a couple years ago, and then we have a lot less problems now with that. Okay, so just don't forget that the surface area multiplier is there, and if you don't use that surface area multiplier, you'll have the wrong answer for that. And especially it's going to be almost 1.6 times it's going to be off really bad with the angular sands. Okay, so the multipliers for different types of sand. We haven't talked much about the different types of sand, but we have olivine sand, which is kind of somewhat going extinct right now. It came from out west. It's volcanic, type of volcanic rock that's kind of crushed and used in usually in non-ferrous situations like aluminum. And there's zircon, which is and chromite. Both of those are very dense, and those usually used for specific applications, usually for chilling or for maybe some facing sand where you want really good surface finish. Okay, so this so you know those multipliers, because it's per gram, and some of these have much different densities. You see the multipliers are going to be very different, especially zircon is 24, whereas silica is 40, because zircon is almost twice the density of silica. So just make sure you use the right multipliers when you're figuring out surface area. Okay, so silica is usually the most common sand, and that's the stuff we have in Wisconsin. It's very pure silica sand. And if it's very pure silica sand, it has a melting temperature somewhere around between 26 and 3,200 degrees Fahrenheit. Now, if we're pouring metal at 3,000 degrees, or even sometimes higher than that, wouldn't we be melting the sand in some cases? Well, remember that the sand grains themselves don't always get to that temperature. Yeah, some of them near the surface can, and they sometimes do melt to the surface, which can be a big problem when you go to clean your castings. There's a density there. The bulk density means when you make sand, green sand out of it, or what is it per cubic foot of sand? Not just the actual sand, one sand grain. If you take the density of it, or a big block of silica will have this density, but the bulk density is okay. Well, if I have a cubic foot, how much is that going to weigh? Okay. And this can change with the binder content and stuff like that as well. But generally, you usually say silica is about 100 pounds per cubic foot. So it's an easy way to estimate the weight of some amount of sand. Okay. It has an expansion coefficient, and it says this low number, 0.018 inches per inch, or 1.56%. And what we're going to show you in a little bit is silica has this bad habit of changing its crystal structure, which also changes its density, which will be a problem in that you'll have possibly some sand expansion defects. So it's slightly acidic. Sands can be either acidic or basic. You put them in the water and they act either in an acid manner or in a basic manner, which is kind of weird, but it is the case. Heat transfer is kind of intermediate. So silica sand transfers heat, not super fast, but not super slow either. Olivine has low heat transfer. And if you look at this, silica is the cheapest type of sand. All these other ones, it tells you many more times expensive it is than the silica sand. So olivine is 10 times the cost. Hence, most people, even though it has this problem with the expansion defects, they still use it because it's really cheap. Okay. So olivine sand, what is it made out of? It's magnesium iron silicate. Okay, so Mg, Fe, and SiO4. Okay, it's kind of a complex. It's a volcanic rock. It's kind of green colored, whereas silica is clear. It's a basic composition, slightly higher density, bulk density, and you can see it has a relatively low-ish, expansion defect, or expansion per, inches per inch expansion rate. Sorry. Zircon, really expensive, and these numbers might not be the same anymore. Zircon's getting really expensive. Has a super high melting temperature, 3,700 to 4,000. So sometimes we do put this as facing sand in order to keep down the melting of the sand near the surface. And very high bulk density, almost twice the density of silica. Zircon is acidic and chromite's basic. Why does that matter? Some of the resins that we use have acid type or acid or basic catalysts. And so if you have an acid type sand and you're using a basic type catalyst, it may not cure because it's acting to the opposite. It's actually counteracting the catalyst. Okay, and then you can see that both of these have a high heat transfer rate, and so what's good about that is we tend to use these in situations where we want to chill the metal. Whereas olivine, we want to use that for aluminum, where we want to have real thin castings, and they'll come out. You'll be able to flow the metal farther. There's a couple other ones that I've never seen used here, so I'm not going to talk much about those. What kind of defects can you get in green sand, or sometimes in coarse sand, but it's usually in green sand. So the silica is inexpensive and lightweight. Why would that be a problem? Well, remember that you're moving this sand all around the foundry, so your equipment is sized to be able to move it around the foundry. And so if you have really heavy sand, you may need different equipment to move it around the foundry. So we want to minimize these expansion defects. So now it's kind of a little bit hard to see here, but the clear area here is sand, and then this is the molten metal coming in contact with the sand. So what happened here in this first one, this rat tail, is this is a side view or a cross section of the casting. And what will happen is the sand cracked and peeled away, and molten metal kind of flowed into this little crack here. Sometimes you get a buckle, and what that is when the sand kind of creates a void behind it, but the metal doesn't penetrate into that void. And then if metal does penetrate into that void, you get this thing called a scab, where you'll have the casting will have like this low spot and then a high, like a chunk of metal stuck on the surface. This could be like a row of material as well. It doesn't. This is not just one little spot. It's usually, especially these buckles, they look like a crack running across your casting. Okay. So those are some expansion defects. And why do you get these expansion defects? Because the sand grains are touching each other, and especially with round sand grains, as they expand, they have nowhere to go if they're under compression. So they have to go somewhere. They just buckle into the mold cavity. Okay. Remember, it's getting really hot, and that material all is expanding. And so if all those sand grains are touching each other and they're all expanding, it's got to go somewhere. So you have to have some give. And we can add things into the sand. We'll talk about it later, but we can add some things in the sand which allow a little bit of room between the sand grains in order to cut down on these problems. Okay, so why do they form? Why do these sand expansion defects form? Well, silica changes its crystal structure at a temperature, and it's hard to read this temperature, but I think that's 1200 degrees right here. This is about 1000 degrees. So, it goes up relatively uniformly up to about 1000 degrees, and then it skyrockets, and then it plateaus, and then it comes back down a little bit. So that's kind of weird. Well, what's going on? Silica is changing its crystal structure. It's going from its normal crystal structure to something called cristobalite, which there's a couple bad things about that. So there's a huge, first of all, there's a huge expansion during heating. And this cristobalite is the stuff that, when it breaks down, can hurt your lungs. Okay? So there's something called silicosis, and silicosis is caused by long-term exposure to particles of silica sand, and it's usually the stuff that breaks down really fine, and it's usually the cristobalite is the one that's the bad actor. Okay, so foundries are particularly, have a potential for causing silicosis. Old foundrymen in the olden days, when they didn't have good ventilation in the foundry, they would many times have respiratory problems in their old age. That's hopefully OSHA has a maximum exposure to fine-grained silica, and they actually just lowered that value by half. So foundries had to put in more ventilation or somehow contain or prevent that breakdown of the sand grains, so you don't have these fines floating around in the air. If you have wet sand, like green sand, it's not a problem, because the green sand, all the moisture is tying those little grains, those particles together. But when you shake out or you mix sand, you need to have you need to wear a respirator or have good enough ventilation that takes it out. So we do have that, and now that everyone's wearing respirators, it's not a problem. As we start to add impurities into the sand, then we start to get a lower melting temperature, and when we get a lower melting temperature, then we have a problem. Okay, so here, as we have not 99% pure silica, we have 94% silica, we go down to 2700 degrees, which will definitely burn on or burn into the surface of the casting. Okay, whereas in Wisconsin we typically have this good stuff here, this 99.8 or whatever, and you can see there's small percentages of calcium oxide, magnesium oxide, these other things. What happens is these other elements lower the melting temperature of the sand. It's just like when you add two metals together, typically that lowers the melting temperature of the alloy between those two. Same thing happens with ceramics, because silica is a ceramic. It's really glass, if you think about it. So as the sand melts, it can burn in or onto the surface. Burn in is actually included into the surface, whereas burn on is just on the surface. So these specialty sands have higher melting temperatures, which can reduce those problems. Angular sands, using a fine distribution, are more susceptible, because they tend to, if they're fine, they tend to heat up more, and it's just, they just melt easier because of the little point sticking out instead of them being completely spherical in nature. So we talked about the impurities already, so let's go to the next one. So here's some other stuff that can happen. So the refractoriness, if you want to increase the refractoriness, which means that it can withstand higher temperatures. If we mix silica and calcium oxide, if they're both present as impurities, chrome oxide sand can be flux. So basically the surface melts, and it's kind of hard to see in this, but metal is here. Okay, this is a micrograph. In other words, we polished a sample. This right here is this glaze where the molten metal has penetrated, and the chromite has kind of formed this lower melting temperature material, and so the metal is kind of fluxed into it, and so we get this glaze on the surface, and it's really difficult to get off. You'd have to grind the crap out of that stuff. And can you imagine when you grind this stuff, it has these really hard particles in the surface. So my abrasives, which are essentially oxides, are trying to remove oxides that are on the surface, and they do break down. By the way, we do use diamond more often. They're using diamond wheels and diamond grinders to start grinding this stuff, and we get much longer life. So that's refractoriness. That's some of the things that can go wrong. But generally, high purity round sand grains give you higher refractoriness. And some of those other specialty sands. Okay, so how about the casting cooling rate? What do sands do to the casting cooling rate? Well, silica sand It's a relatively good insulator. It's kind of in the middle. So liquid metals cool slowly. Olivine is even slower, so it doesn't pass heat through it quite as quick. So what happens is you can flow metal farther. We can have less mist runs. Remember, a mist run defect is when the metal doesn't fill up the cavity completely. Okay. And chromite and zircon do the opposite. So we sometimes use those for a chill material, and we use them just in the face of the sand typically. So we just put them near the surface of the mold. If we use zircon, so olivine, we just said a second ago, doesn't transfer heat quite as fast, but zircon does a completely different thing. Zircon is not wetted, so in other words, the metal just kind of runs across the surface like you just waxed your car. Okay, so the metal runs across the surface, and so it actually can flow farther because there's not friction between the mold and the molten metal. So when we put zircon, or sometimes we put it on as a wash. What do we mean by a wash? We spray it on the surface of the mold and with really fine-grained particles. So we might do a facing or a wash with the zircon. It's really expensive again, and we usually lose that material because it just gets mixed in with the green sand. It's hard to reclaim. One thing you can do with chromite sand is you can reclaim it magnetically, but you can't do that with zircon sand. Okay, so that's the fluidity of the metal. The pH of the sand. Again, if you put the sand in water, it will either act like an acid or a base. And so there's a test called the acid demand value, which will either add we add sodium hydroxide or we'll add acid, and essentially how much of each of those gives you how basic or acidic it is. Okay, this is important if you're using resins that are sensitive to whether they're acidic or basic. And then also green sands will also, sometimes we actually add things to change the pH of the sand in order to get a stronger bond. Now we're going to talk about clays for sand molding. And so clays are basically the binder that we have in green sand. So we want to use the right kind of clay. Now there's all kinds of different clays. As if you've ever played with pottery or whatever, usually you're using something like a fire clay, kaolinite, which is it can be used, but it's not very effective. It takes a lot of clay, and it's not very strong. Naturally, there were reserves of sand. It's called naturally bonded sand. We don't use it anymore because all the mines are shut down. But you could just dig up sand and clay. It was usually like the fire clay type. It wasn't bentonite. So in the old days they called it naturally bonded sand. Now they used then when they started mixing sand using bentonite clays, they would call that synthetic sand. But now we just all green sand is pretty much synthetic sand. The naturally bonded sand, if you look at some of the old castings, they could get really fine detail with it. And it wasn't about the strength, it was more about they could use really fine sand grains with the kaolinite, and it was really cool. They could dig it up just out of the ground, and different layers would have different grain finenesses. So if you wanted coarse stuff, you would just dig it out of a different layer. Kohler used to make their hot tubs using naturally bonded sand until about 15 years ago. I remember one of the last times I was, they were the last company I don't know if in the world, but in the United States that was using that kind of sand, and they literally were making a mold that was about 5 foot, 6 foot square, even bigger, to make a whole hot tub as a one cast iron casting. Pretty cool stuff. And they would get better surface finish with that. I think now they're making them over in China. I'm not sure how they're making them. You can still buy a cast iron hot tub. They're pretty nice, but they're very, very expensive. So bentonite, montmorillonite, it's called, is the most commonly used. It's stronger than fire clay, and there are two general types. If you remember from the lab, if you've done it so far, we use Western and Southern in our lab. So Western bentonite is sodium montmorillonite, and Southern is calcium. So I do want you to remember which one is which. So the sodium bentonite is Western, and the calcium bentonite is Southern. And why? Well, Southern bentonite typically comes from Alabama area, and Western bentonite comes from out in Wyoming. Okay, so what actually is clay? Clay is these little platelets. If you look off to the right here, you see these little flat platelets. And by the way, they're really, really small and really, really thin. I believe they're like just a few nanometers thick or 1 nanometer thick. So they're so thin, but they're kind of like graphite. They're similar. They're kind of strong in two directions, but really weak in the third direction. And so they're kind of tricky, what's going on here. But essentially, we bond these either sodium or calcium to the surface, and that's what helps bond the water. Okay, so water bonds sticks to the surface of these clay platelets. And so what happens is they swell. Okay, so here's kind of this is what a clay platelet looks like. It's like 500 nanometers long in this case, and then it's 1 nanometer thick. So what happens is these will get suspended in water. They don't like just the Brownian movement of the atoms in water will keep the clay suspended in solution. So if you put clay and sand into water, real fine grains of sand, the sand will sink to the bottom. The clay will stay floating around in there. Okay, even after you let all the sand grains have settled, the clay is still floating around in there. And that's the basis of one of the tests to figure out how much clay is in the sand. So the aluminum ions are in the center. There's clay platelet replaced by magnesium ions. A charge imbalance is created. Okay, so you have aluminum or magnesium in here. And so these sodium or calcium ions can bond to the surface of it. And then the water platelet bonds to those. Okay, so they have different properties, the different types of clay. Western bentonite usually is used more often in iron operations where you're going to have high temperatures, so that you have dry strength. Okay, Southern bentonite is used in lower temperature materials, typically where you need a lot of green strength, which would be stuff like aluminum or brass. And so, but you might do a combination of the two, and then get some of the benefits of both. They even take like a Western bentonite and they add some calcium ions to it to try to make a blend that, well, why would you want to make Western more like Southern? Because Western, it doesn't have very good green strength, but it has really good dry strength, whereas Southern has good green strength, but not very good dry strength. Okay, so and also Southern bentonite has good collapsibility and flowability. You're going to try to move the sand around the foundry through conveyors and things like that. If it doesn't have good flowability, you can't blow it into a mold. You can't mold it very well. Bentonite gives it the Western gives it toughness, durability, and that hot and dry strength. Okay, so that's why we add both, because we do pour just about every different alloy in our lab. What are the properties of different bentonites? Western bentonite is caustic or basic, whereas Southern bentonite is acidic. Okay, And you know, when you heat these materials, they start to soften at different temperatures. Now remember, if we bake, the softening point for kaolinite is a very, very high temperature. Look at that, 3,000 degrees. So that's why it takes such high temperatures to make pottery and that kind of stuff. Okay, but it's not as good for green sand. Okay, so very high gel forming. That means that it swells up in water. In fact, they put Western bentonite. They'll typically put it in a pond if you don't want the water to go through the earth. They also use it in the bottom of what do you call it? Like a dump where you don't want, or if you're trying to contain chemicals in a dump, they'll put it in the bottom and they'll line the bottom with clay in order to keep those chemicals from contaminating the area around it. Okay, so lots of different terms. Durability. So green sand gets used over and over. So the durability is to be able to keep on absorbing that water time and time again without losing its effectiveness. Otherwise, what happens is the clay is said to die. It's still there. There's the platelets are still there, but they die. They don't have any more bonding capability. They can't hold water. So the ability for the clay to attract the sodium and calcium is this thing called base exchange capacity. So a high base exchange capacity means that the clay will be effective at bonding, bonding first of all the sodium and calcium, and then also bonding the water to the surface. Clay needs to be activated, so mixing it with sodium carbonate can cause the calcium ions to be replaced by sodium ions, thus making it behave more like Western bentonite. And so what I meant by that, by activated, it has to be activated if you want to make your clay that's a Western bentonite more like Southern, or Southern bentonite more like Western. So they can try activating it with one or the other. Okay, it's still not as good as actually mixing the two together. Degrading is this loss of, you know, the structural change. So it degrades when it, you know, when it's lost its durability. It's degrading, melting, or changing its crystal structure and being less effective. So the deal is, the higher temperature we get the sand, the faster it breaks down. And so as we increase the amount of metal for how much sand, or let's say the sand to metal ratio, as there's more sand and less metal, then you don't have to add as much clay. You don't have to add as much sea coal, which is it keeps the metal from sticking. It's an additive that keeps the metal from sticking to the sand. And you don't have to add as much new sand. Why do you have to add new sand? Because the sand grains break down due to this thermal cycling. So if we have a 3-to-1 sand to metal ratio, and this is an example, you might have to add 100 pounds of new sand into the system per mulling, or per some, you know, per ton, or whatever it is. I'm not sure what the units are here. But at a 20-to-1, you only have to add 15 pounds or percent, or whatever that is. Okay. And you have to add much less clay. Clay is very expensive. Also, the amount of sea coal as well. So if we keep a high sand to metal ratio, we don't melt the sand grains, we don't burn out the clay quite so much, we don't burn out the sea coal, and we don't have to add as much new sand. Okay, so the durability goes up if we use more sand and less metal in the mold. Of course, that's not as efficient. Okay, so here is an example of how clay actually acts, or how, you know, a representation of that. So what we have is this clay platelet, which has the sodium ions attached to the side. This must be a Western bentonite. And then here, these little blobs on the side are the water molecules. And in this case, we have kind of like one set of water molecules around this clay platelet. This one also has one set of water molecules around the clay platelet. And these tend to stick together because the dipoles on the water help them stick together. Okay. So and we have a charge, by the way, also on the sand itself. This electrostatic charge is what also holds it together. So this is a sand grain, that's a sand grain, and this has 2 layers of clay in between. What's the optimum? Okay. So the properties of green sand are determined partly by the number of layers of water molecules on each clay platelet. Remember I said that 30% moisture as 30% of the clay percentage as moisture you get the best green strength. Okay. If you, as you go above that, you get a higher density because there's extra water. If you go to even more layers of water, you get really good hot and dry strength. So if we go really high on our moisture percentage and then we dry it out, we can make a really strong, dry sand. That's what they used to do before they had chemical, resins. They used to basically make sand with I think it was 15 or 20% water, and then they would dry the mold out, and it would be really strong. They don't do that anymore. Okay, so what we're looking for is 30% of the percentage of clay is what we want to do as the moisture percentage. And don't forget, other things will tend to absorb water, like fines, and like some of your other things in there, like additives. They might be fine particles, and they will absorb some moisture too. So we've got to be careful on that. So here we have too little water. There's some clay still available. So the clay platelets plug up between the sand grains, and this is clay and water on the surface of each. And we'll have a low permeability on this. Okay. Here we have the perfect amount, and then we'll have voids between the sand grains, so the permeability will be at its maximum. If we have too much water, then water fills in between them, and now we will have a poor permeability again. So same thing with green compressive strength. We know this because I've talked about this a little bit in class already in the lab. But as we go to higher percentages of water, we get a peak. It doesn't say, oh, this is 9% clay. So around 3% water, we're going to get our peak of the compressive strength. Okay, it doesn't say what the green compressive strength is, but here we have the permeability is at its highest, right around the same percentage because of that exact science we were just talking about. Now, as we put different amounts of clay in, we're going to have different. Now, this is, by the way, this is the graph you're going to need for your lab because you're going to want to compare what you got to this graph. It doesn't say here what type of clay this is, so we're doing 50-50. So you might, I don't know if this could have been calcium bentonite, so it might be a little bit stronger in green compressive strength than what you get. But usually this turns out really close to the answer we get. Depending on if we did the lab right, we have the right composition of clay, then you should get a peak, and then we try to bridge that. It may or may not have worked depending on which year you're doing this in. This last year we were only at 5%, so we ended up being way off here, in fact off the graph a little bit, and had pretty low compressive strengths. Sometimes we get into the 16 and the 20s once we're up into this 7 or 8% of clay. So again, about a 3-to-1 ratio of clay to water. Notice that above 12% clay, we don't really get any stronger because now you have so much clay that the clay is plugging up between the grains. It's just like when you get too much water in clay, it ends up sliding. So the sand grains are kind of sliding over each other instead of the sand grains kind of being close enough together that they actually impinge on each other slightly, and there's friction involved in that. Okay? So also, as you go to a high percentage clay, you're more likely to get blow defects because there's just so much water in the mold. So one of the things you're going to do is calculate the density of, in that lab, is you're going to calculate the density of that 2-inch by 2-inch diameter sample. And generally, the density also is the lowest when you have your maximum void space. We just talked about that a second ago. Highest permeability will also be the lowest density. So when we have our 3-to-1 ratio, well, we should also have about 100 pounds per cubic foot, and it will be the lowest density of our sand. Okay, so you can actually plot density is one of the things you can do in order to plot your sand. Okay, so some of the additives we might add to sand are carbon. Why do we add that? Because when we put, let's say, iron into a mold, it's going to want to form iron oxide. If it forms iron oxide, that combines with, it fluxes the silica on the surface, and now we have burned on sand. So what we do is, if we remove all the oxygen from inside the mold, it can't form iron oxide. Or silica. It sometimes even forms silica on the surface of the casting because there's silicon in cast iron. And therefore, if we burn up all the oxygen inside the mold, then it reduces that burn on. It works actually very good. Okay, next thing is we can add some cellulose. That reduces the amount of expansion you get from, well, it reduces the expansion defects. Why? Because wood flour will form little particles in between the sand grains. And as the sand expands, that wood flour will tend to either crush or to burn out. So the sand grains have some breathing room, they have some expansion room. Okay, so that's why we would add cellulose. It also improves the flowability as it moves throughout the foundry and can improve the surface finish. Cereal or corn flour we would add for a little bit better toughness. Sometimes when we pull the pattern out of the mold, the edges tend to fracture right there. So it's kind of like glue. We add a little bit of extra glue in there, and that cereal then helps to make the mold more tough. Okay, silica flour to increase density. I believe that helps with the surface finish a little bit. I've never seen anyone actually using it, but you could do that. Iron oxide can reduce veining, making it's just keeping the mold from cracking is really what happens. Okay, so some people add iron oxide to it's usually coarse sands. We add that. So now we're going to talk about sand testing. So we talked about the sieve analysis already. The moisture content is an important test to figure out how much moisture you have in there, so that we keep that 3-to-1 ratio between the clay. Mold hardness, we talked about that a little bit. Permeability, again, and then mold density. Green compressive strength is an important one. And so let's learn a little bit about another one called compactability. So hopefully you don't get this confused. I know it's very confusing, but you use the same 2-inch diameter by 6-inch tall sleeve. You basically fill it to the top with riddled sand, and then you strike it 3 times, and then you look at how much change the height was from when you had the 6 inches in there to afterwards. Okay, so the compactability is that change in height. So a higher compactability means that the sand is fluffed up more, and a lower compactability means that it doesn't have as, usually it's proportional to the moisture content to some extent. Okay, so the optimum somewhere around 45%, but it does kind of depend a little bit on what kind of molding machine you're using. Combustibles, what is that? Well, earlier we talked about putting some sort of a additive to the sand that's going to give off carbon monoxide or somehow break down and keep it from sticking. But we want to know how much is still in there. And one of the ways to do that is to, wash the sand, get all the clay out of it or whatever, and then to burn off and dry and then burn off the rest of it. So basically, the sand additives burn up at a relatively low temperature. Combustibles is usually at 900 degrees Fahrenheit. And volatilized means that, it might have some chemicals in there that come off as you heat it. So when we volatilize it. So basically you take a dried sand, you put it in the furnace, usually at 900, to volatilize everything that's in there, and you reweigh the sand afterwards. I may have said something like you wash it. You don't. You just dry it. Sorry. So it measures the amount of things like cellulose and cereal, which tend to burn up at that temperature. Collapsibility and other properties are proportional to these things. Now, sometimes we want to find out the total combustibles. Okay, so there's other things that burn up at higher temperatures. So we do this at 1800 Fahrenheit. So it burns up all the combustible materials, even the carbon. Okay. So basically, you weigh it, dry it, weigh it before, weigh it after, and it's also called loss on ignition. And if we look at the difference between the total combustibles and the percent volatiles, we figure out what the carbon content is in the sand. Okay, so basically, sea coal and other carbon additives don't burn up at the lower temperature. And we put those in there typically for iron type of castings. So how do we measure the clay content? Well, the clay is measured two ways. One is we can get the total amount of clay that's in the sand by, remember earlier I said that the platelets always stay suspended in the liquid. So we have this little thing here, and what it does is it takes your dried sample, and you, by the way, you're gonna take and take your dried sample and weigh it, and then you're gonna put it into this beaker. The beaker will fill up with water. It'll kind of blast the water around in there a little bit. All the clay, hopefully, will get pushed off the sand grains and be floating in the liquid. We'll let all the sand float to the bottom, but the clay stays in there. And so it just keeps on doing that many, many times. And so all that stuff, all the clay floats out. And some of the other things, too, that throws it off a little bit. But the clay gets removed, and then we weigh it again, and we get the total clay, or the AFS clay. But what the problem with this experiment is it doesn't tell us actually how much clay is bonding, because it measures both the dead clay and the live clay. So AFS clay gives you the total clay that's in the sand. A methylene blue test tests to see how much live clay or active clay is in the sand. And it's a long procedure. We normally do this in lab. But essentially what you're doing is you're using this dye, and the dye gets, let's say, absorbed by the clay platelets. But at a certain level of dye, the clay platelets can no longer absorb this methylene blue solution. And so what happens is if you drop it on a piece of paper, if it is completely absorbed, it just makes a little blue dot, kind of like you see here in this little thing above. But as you go to higher and higher concentrations of that methylene blue, eventually you get this thing called a halo. And there's some, we kind of look at, you know, it's it's usually the second one that produces the halo. There's an endpoint, okay? So we get this halo around it, and then that's how many milliliters that you took to titrate it. And then you have a reference standard that you use that you said, okay, well, there's, you know, 8% clay or 1% clay per milliliter or something like that. And then you can actually figure out what that is. It's usually the number like 5 milliliters per percent clay, something like that. Okay, so whether you do this experiment or not, you know, the idea is that you understand what the methylene blue tells you. It's telling you how much clay is actually actively participating in the bonding. So if you knew the live clay and you knew, or the active clay, and you knew the total clay, you could subtract the two and find out how much dead clay was in there. Okay. Once you have some of this data, you can put it into a little graph that we have, and it tells you two things. One is the working bond and what the available bond is. And the working bond is how much is actually contributing to the bonding, okay? Whereas the available bond is how much could be could be activated. So the total and available bond are calculated from a special graph that I'm going to show you in a second. It's calculated by using, let's see, a working bond is the amount of clay that's been properly reacted, depending on the amount of clay, sand, water present, and how the sand has been mulled. The deal is, if you have a certain amount of working bond and a certain amount available, depending on how well the muller is working, the higher the working bond is compared to the available bond, the better your muller is working. So what we're going to do is look at this chart here and see how we calculated this. This is the IMC control chart. This was actually developed at Brilliant Ironworks, which only closed a couple years ago. So we have our green compression strength over here. I don't know, let's say we have a value of 20, okay? And we have, let me see here, this is the, on the bottom is percent compactability, okay? And so if we have a 45% compactability and we have a 20 of the green compression strength, puts us right here, and then we follow this graph up and we have a 3.5% working bond then, okay? And that would be like the clay percent that's working. Now, if I determine the moisture content, I don't know, let's say we're at 3.5 moisture content. Okay, we go up, and then we're also going to use green compression strength again. So we come over here at green compressive strength, and we were at 3.5%. And so we follow that up, and it's something like 6.8, I think that is. So 6.8 versus 3.5. Okay, so the molar efficiency is 3.5 divided by 6.8, which is about 51%. So that's you know, relatively normal. This is something that you're going to want to calculate when you're doing your lab. Okay, so you're going to need to see that graph and actually use that. So right there, molar effectiveness is equal to the working bond over available bond times 100. So 50% is okay, up to 80%. I think ours runs kind of a little higher than the 50%. 100% Muller effectiveness is impossible. Some of the clay is not available for bonding because it's not it's just coating the whole clay, the surface of the sand grain, and it's not actually touching another piece of clay. If it's less than 50%, something happened. The Muller broke, the wheels are frozen, something's going on. So you'll have to go and do some maintenance on your Muller probably. We did this in the lab. If you want to measure how well the sand's being prepared, you can monitor the power it takes to mull versus time. And so you can use some relatively sophisticated mathematics to figure out, or signal processing to figure out when the batch is done. And Neenah Foundry saved a lot of money by using this. They call it mull to energy. In other words, they're mulling the sand for the amount of time it takes to just get the clay mixed with the water and get it, distributed. So, and then they look at that over time. They look at the power required, and they can tell exactly when you want to dry. You actually can reduce the properties if you overmull sand. You can't actually damage the sand. So that sand to metal ratio is important also for the temperature that the sand's going to get. If you have not enough sand and too much metal, eventually the sand, unless you have some really good cooling systems in the sand system, they do have sand coolers, but they can only do so much. And so once you go above like 140 degrees, you have poor mechanical properties of your sand. So you need to have them below about 140 degrees. If you get above like 140, 150 degrees, the moisture is given off so quickly you can't even make a mold before the moisture in the sand evaporates. So you need a big capacity and allow time for the sand to cool, and then keep your sand to metal ratio high enough that you don't overheat. And this obviously will change relative to what time of year it is. In the summertime, it's going to be a lot harder to keep your sand cool than in the wintertime. If you can imagine you're down in Georgia or North Carolina or even Alabama in a foundry in the middle of summer trying to cool your sand down, it's not easy to do. They also have high humidity there. So this kind of concludes the part one of sands. I know it's a long haul here, but next thing we're going to talk about is actually core sands. But get yourself familiarized, read through the sections in your book, both the TAN book and the handouts I gave you that kind of follow along with this PowerPoint, and take some notes during these presentations because this information will show up on your labs and on tests.